Hello there guys, welcome back to another epic inexorable maths video. In this video we're in a brand new location. What a stunning place. Secret location that I can't disclose where we are. But in this video we're looking at the first time double integrals. And double integrals are actually really cool. So let's just dive straight in, let's not dilly-dally with it. Let's just go straight into our intro to how to evaluate and explaining what they are. Double integrals. So I've got a few things here. First of all, this thing is an example of a double integral. So you can see here that we have basically a function in the integrand of several variables, two variables. It could actually be, if this was a triple integral, three variables. It doesn't really matter, but right now we're just doing double. So this is our integrand. The way that you understand what this means is you look at the kind of internal integral first. So the integral from 0 to 1 of x squared y cubed dx, get the value of that. Once you've got that value, you then take that and you integrate that with respect to y from 2 to 3. So you kind of look at it from the inside and out. And if it was three integrals, there would be a dz here, there would be another integral out here, and you would just do the process as many times as you need to. So that's kind of the idea of like what it is, how you evaluate it. We'll evaluate this one in particular in a moment. But first of all, I want to explain what a double integral really is geometrically and just interpretation-wise. It's quite important to know how do you actually deal with these double integrals? How do you kind of explain them in your head? So let's just go back to normal, typical integration for a moment. So normal integration says that if you have an integral, for example, of, let's say, x squared from 1 to 2, then what this is, the value of this is the area of, and this is the graph, of course, of y equals x squared. And of course, I should technically say this is the x-axis, even though maybe it's obvious, and that's the y-axis. This is the area beneath the curve y equals x squared from the x-coordinate 1 to 2. So these are x values here. I know that everyone knows that, it's obvious, but it's important because double integration is kind of analogous in a sense. So I'm going to try and draw you guys a picture, but I don't know how good it will be. So now we're in 3D because what a double integral does, unlike a normal single integral, is instead of giving you the area under a curve, it gives you the volume under a kind of infinitely thin 2D plane, and it could be curved, it could be all sorts of weird shapes. So if we label this our x-axis, y-axis, and z-axis, the z-axis is of course a new thing. So all of these are perpendicular to each other, it's just 3D kind of coordinates. You may be familiar, you may have seen this before with vectors or all sorts, but let's not get into it too much. This is a three-dimensional situation right now. So if, and let's actually take the example that we did earlier. I don't know what the graph of z equals x squared times y cubed looks like, so I'm not going to try and draw it, but I'll draw a representation of it. What I do care about though, and this is the important thing, is the limits. For double integration, and actually any integration for more than a single variable, it's really important to know what the limits are, because what you will see is that the limits are going to stop being constants. They're going to be functions. So not right now, but in a moment, or at least in the future, in future videos. Right now they're constant, so it's nice and easy to kind of explain. So again, what this is telling us is that 0 and 1 are x functions, they're functions of x, whilst 2 and 3 are functions of y. That's because you evaluate the internal integral first, so it's dx. These limits must be in terms of x. And then the exterior integral is, of course, in terms of y. So if we look at our kind of bounds of integration, normally in single variable, and this is kind of why I drew this earlier, in single variable integration, your limits are just lines. So you integrate between the lines. But with a double integral, what's really important is you're not going to be integrating between two lines anymore. You're going to be integrating between two lines and then another two lines. You're going to create boxes and squares and circles and any shape really that you want to bound your integral, because it's going to be a 2D situation. So let me explain what I mean. If you take the integral that we just had, the x limits were between 0 and 1. whilst the y limits were from 2 to 3. So it's like, well, how do you actually consider, what is that? Well, it's this. So if you imagine the area that is bounded with x coordinates from 0 to 1 and y coordinates from 2 to 3, then you will have, that's not a very good drawing, you will have this square here. It's a square. So that is the square such that the x coordinates are bounded between 0 and 1, the y coordinates are bounded between 2 and 3. Now, we haven't actually drawn the function on. And remember, the function was x squared y cubed, so we need to add that. So if our function is z equals, and it's always going to be a z equals x squared y cubed, again, I don't know what it looks like, so I'm not going to try and draw it, but it's going to be some sort of 2D situation that's kind of floating around. I don't know what it will look like, but what I do know is that it will form some sort of shape above. And so what we'll get, if you imagine this kind of strange shape that I've drawn, if you imagine it as like the ocean, the top of the ocean, the top layer of the ocean could be your function, right? What you want to do, and this is what double integration really is you're trying to find the amount of water directly below the top area of the ocean. And the kind of region that you're bounding, that kind of square or rectangle that you're trying to find the amount of water above or below, that's your region. Those are your limits of integration. So we're trying to find, again, if you imagine this was an entire ocean, we're trying to find the amount of water, the volume of water between x coordinates 0 and 1 and y coordinates 2 and 3. And the value of that double integral that we've got here, this will be the volume of water. That's really what a double integral actually is. So I hope that's a kind of valid explanation. So, so let's actually do it. Let's actually evaluate this integral and see what it's like. So the first thing that we're going to do is we're going to leave that exterior integral alone. We're then going to look at the internal integral. And this is the kind of thing that you have to do. This question in particular is quite straightforward because if you're integrating with respect to x, just like if you've seen partial differentiation, the y will be constant, so you can just ignore it. You could even take it outside of this integral because we can just integrate x squared. But we're going to pretend that y cubed is a constant. Maybe you want to call it a cubed or c cubed or something like that. So I'm going to leave y cubed as it is because it's a constant. And because I'm integrating with respect to x, I'm going to integrate x squared, which is a third x cubed. I'm then going to evaluate this between our limits, 0 and 1. And I need the dy on the end. That's just there for later. Okay. That's the first step. Then we can probably evaluate this, simplify it a little bit. So this goes from 2 to 3. And this thing here, well, again, this is an x limit. These are x limits. So I'm going to let x be 1. So this will be y cubed times a third. And then when x is 0, it's just all 0. So this will be y cubed over 3. That's it. And then there's the dy. And now you just have a single integral, which hopefully we know how to do. This is going to be y cubed, that will become a 4, and then we'll divide by 4. So we'll get y to the 4 divided by 12 from 2 to 3. And then we just evaluate this. So 3 to the power of 4 is 81. So that's 81 divided by 12. Minus 2 to the power of 4 is 16. So 16 over 12. And then you could work this out. You could simplify it, etc. But it doesn't matter. The answer to this would be the volume of this kind of cuboid shape with a weird top. That's basically what it is. That's what double integration really is. So obviously, as you can probably imagine, double integration can get very complicated, just like how single integration can. And there are methods where you can do all sorts of fun, crazy, exotic things in order to help you work them out. they're not exactly the same as normal integrals. There's things that you can do with double integrals that you can't do with normal integrals, and we'll see that in the future. But I hope that's a kind of reasonable explanation to what a double integral is. It's not amazing because it's difficult to draw, but really try and focus and visualize what it is, and hopefully you will succeed. I'll make lots and lots of double integral videos coming to you in the future. So look out for those. We'll do some examples. We'll get some really crazy ones, and it should be fun. So thank you guys so much for watching. I highly appreciate it, and I'll see you in the next video.